Hello. Thank you, Barbara. So I'm Brice Rauby, and I will present some research about sparse neural networks for ultrasound localization microscopy. This research was done with the support of Ivado and TransMedTech at École Polytechnique de Montréal, and under the supervision of Maxime, Gasse, and Jean Provost. So first, you need to know that ultrasound localization microscopy relies on the precise localization of microbubbles that are injected into the bloodstream to map the vascular network at a very high resolution. This allowed this method to combine the advantages of conventional ultrasound, which are to be portable, non-invasive, and non-ionizing. And through this localization of the microbubbles, you can deduce the position of blood vessel at a very high resolution. However, this requires to wait long enough for all the microbubbles to perfuse the whole vascular brain, the whole vascular network. So this acquisition time is a limit to the extension of ultrasound localization microscopy to clinical use. Recently, some deep learning approaches have allowed to reduce the acquisition time as they better model the microbubble interaction, and therefore you can increase the concentration. In some recent work in our laboratory, we introduced a spatiotemporal neural network that allowed to reduce the acquisition time by a factor of 2. However, these methods are limited to 2D imaging due to graphic memory constraints of the neural network. So therefore, we developed more efficient deep learning approaches that could be applied in 3D, but they were limited to in silico study and did not perform well in vivo. In this lighter approach was very easy to use in 2D, but when it comes to 3D imaging, it was difficult to train and difficult to tune all the parameters. So the performance were poor in the in vivo application, and the region of interest that could be imaged was reduced. All these deep learning approach are based on the same framework. So we train the neural network on simulation data. Those simulation data are obtained through a real vascular architecture that are obtained from mouse brains that are imaged in vivo. So from this vascular architecture, we simulate trajectories of microbubble in those blood vessels, and then simulate their ultrasound response. And therefore, with their ultrasound response, the image we obtain, we can compare the input with the trajectory, the original trajectory that we have simulated. So as you can see here, the simulation input is quite different from the in vivo input. So this can cause the model to underperform. So we use a correlation threshold that remove all the parts of the image that are not likely to be a microbubble. Therefore, we obtain images that are mostly black. So most of the image does not have a lot of information. So this kind of neural network aims to increase gradually the resolution of the image. So starting from a very coarse resolution with big pixel and coming down to a finer grid. And also we use a temporal context, as I said before. So you can see here the 500 time steps that are represented in this direction, and at the output we want only one image. So that's why it's flat. So successfully applying convolution and activation and also upsampling to increase the resolution, we obtain this high resolution map. But this is very expensive in terms of memory footprint, because you have to store all the information of the intermediate volumes. That's where, as it is a great solution to reduce memory consumption in some case. Indeed, let's take the example of this trajectory and represent it as an image. You can image it on. So the white pixel will be where there is some trajectory. So if you represent it as an image with a dense formulation, it will be 64 pixel, 8 by 8. It's easy to understand. The Sparse formulation, also designed as CO format, only store the value that are non-zero. So here we have 10 pixels, but to retrieve all the information, we need also to store where those values are. So it will be 20 coordinate value to store in addition. So another advantage of this sparse formulation is that it scales better when we increase the resolution or the dimensionality. For example, let's take this trajectory represented in low resolution with a coarse grid. So you see the difference between dense and sparse is not very big. And since we have to store the coordinate, it might not be worth it. So if you take the same example of a trajectory, but represented in a very finer grid, the difference is much more convincing. In the meantime, if you want to increase the number of dimensions, let's say at first we consider an image, so in 2 dimensions, like this example, and we want to add the time dimension, we multiply by each step of time. And then if you want to add another dimension, let's say if you want to do 3D imaging like we are, it will scale by another multiplication. And this is an exponential scale in the number of dimensions. And we all know that exponential can grow very fast. Whereas in sparse formulation, it scales linearly by the number of pixels to represent the trajectory. So doing so, we can still face an issue. Indeed, the neural network doesn't really know where the trajectory is. So for the input, we can, with the correlation threshold, remove all the error value. But when we will increase the resolution, the number of pixels to consider will grow, because 1 pixel will become 16 pixels as we increase the resolution by a factor 4 in 2 dimensions. So to prevent this issue, we can use the pruning operation. So neural networks usually compute a latent representation at each step of the pipeline, and so we introduce intermediate pixel classifier that will just say if each pixel that are currently considered should be kept for the following operation in the pipeline. So let's take this example. We have a lot of pixels to consider because we increase the resolution from previous step. So we use the pixel classifier, and you can train it with an intermediate supervision. It says only keep those pixels. So we just go back here and remove all the unnecessary pixels. Of course, we lose a bit of information, but this really reduces the memory consumption. The whole pipeline looks like this. So you take a very coarse grid, especially with a temporal dimension that is of 500 values, and we reduce the temporal dimension and increase the grid. We increase the resolution in the grid, and doing so, you do it gradually using this pruning operation that are using references for intermediate supervision. The main benefit is that it reduces the memory cost, but also that no additional information can be added by the neural network when we increase the resolution. This means it cannot detect a bubble in the middle of the pipeline. So first, we wanted to check that pruning does not hurt the performance too much because we are removing information. That's why we are doing this comparison. So this is a simulated comparison between reconstructed angiogram with our methods. So you can see that dice coefficient that measures the performance are very similar, and that the image looks very alike. The memory requirement for an in vivo application using this model is considerably reduced. We also compare it with our previous work. So DeepSTULM, that was the first one that was only applied in 2D. And you can see at this time that all the dice are very similar, but that our memory consumption was really decreased. To validate our approach, we transfer it in vivo and check that the results are similar with light STULM. That was the currently best method in vivo for the in vivo application. You can see that in big blood vessels, the intensity is kind of less important with our method at the right, but that the very small blood vessel like here are a bit more well detected. So if you have to take home a message, is that we are using a sparse formulation and a pruning thanks to our intermediate supervision. The future work will focus on the estimation of the microbubble speed, such as this work by another student from our lab, and also to apply it in 3D. Thanks for your attention, and thanks all the partners for their support. And thank you, Ivado, for the organization.